Hi everyone, in this video we're going to continue working toward our goal of finding the derivative. That's the whole big thing that we do in Calc 1. So in this section we're going to start to talk about the tangent and velocity problems, which are just a really small step from what we were doing with our function review. And there's a relationship between the tangent line problem and the velocity problem, so we'll actually kind of work at that first. So a tangent line, just to be clear, is a line that just touches our curve. So we've already talked about secant lines. If we pick 2 points and connect the dots, that's called a secant line. A tangent line would be where we pick a single point and we draw a line that just matches up with the steepness of the curve at that point, and that would be our tangent line. So this first exercise, this first page, is a preview exercise, which means this would be a really good time to pause and work through some of this, think about it just a little bit on your own, and then come back and I'll zip through and move on to new stuff. But I like to have a little activity whenever possible to kind of get your brain on the same page as mine. Okay, so in this problem we have a position function, s of t. This gives the height of a ball after t seconds. And we're supposed to just check this graph out that shows us the first 3 seconds. And first we're supposed to describe the behavior of the ball over the first 1 second and then from 1 to 3 seconds. So over the first second, really what I'm looking for is that you recognize the ball started off at 48 feet high, and over the first second its height is increasing, and then from second 1 to second 3 the height is decreasing. Right at second 1, we've just hit the peak, we've hit the highest that the ball will go. And I do want you to be clear that this is not a picture of the path of the ball. The ball could very well go straight up and then come straight back down. There's nothing that says it arcs out like this. This is just time and height. Okay, so here's where we get into it a little bit more. Don't mind my wobbly light. We get this expression, I've called it AV. And AV, let's see if I can get you to see all of it at once, is defined to be equal to s of 1, remember this is our function s right here, minus s of 0.5 over 1 minus 0.5. And I'm hoping that immediately stands out as looking like one of our average rate of change or slope calculations. So let's figure out the value, and then we're supposed to figure out its units and its meaning. So s of 1 looks like it's about 64, that's right at the top. S of 0.5 is 1 tick mark down. It looks like our tick marks are 484, so 56, this would be 60. And 1 minus 0.5 is just 0.5, which means we have 4 divided by 1/2. Dividing by 1/2 is the same as multiplying by 2, so we're going to get 8 out of this thing. So this AV thing is equal to 8. If we want to get the units out of this, we can just look at what we just did. We basically calculated the slope of the secant line that goes through these 2 points. So the 4 is the change in y, which in this case is height in feet. So this is change in height, which were measured in feet, and the 0.5 was the change in t, which is time, so this is change in time, and that's measured in seconds, which means the 8 will have units feet per second. So basically what you're getting here is the change in height over the change in time, which is average velocity. So that's why it's actually getting this new abbreviation AV. We won't use that one a ton this quarter. I'm not super concerned if you don't remember it, but it is kind of convenient to have these abbreviations. So the meaning of this thing is that the average velocity of the ball from 1/2 second to 1 second is 8 feet per second. So over that little short time interval, the average velocity of the ball was 8 feet per second. And I actually want to, I'm getting off the bottom of my page again, do a little bit of a generalization here. I would like it if we would realize that in general, anytime our function is a position function, its average rate of change will be an average velocity. So in general, if s is a position function. This means it could be distance or height or anything that tells you about where an object is. Then the average rate of change of S on a B, an interval AB, which is calculated as usual, S of B minus S of A over B minus A, gives average velocity. So again, this is anytime, which we're abbreviating A sub V. Anytime you start with a position function and you calculate the average rate of change, what you're getting is an average velocity. Okay, so let's move on to another page. I want to actually crunch through a few more of these. We'll try and make it not too slow. So here, let's see if we can sneak the picture in. Okay, so I want to, basically what I'm interested in this problem is what's going on around, oh, that's not it, that's 0.5, 0.8 seconds, so around right here. So I'm going to look at some intervals. I'm going to look at the interval from 0.4 to 0.8, 0.7 to 0.8, 0.79 to 0.7 or to 0.8, and I'm going to see if I can calculate some average velocities. So this is somewhat of a calculator problem at this point. Before we got lucky and we had really nice values. Uh-oh, I'm getting low batteries. But this is not so nice, so I'm just going to plug our function in. It was 64 minus 16 times t minus 1 squared. Okay, and then we had a great window before, so I'm actually going to just use that exact same window. So I'm going to hit the window button, and I'm going to set my x-min to 0 and my x-max to 3. So that's what we were looking at before, 0 to 3 on this graph. And then I'm going to, x scale is how far apart your tick marks are. Those can be 0.5 to match my graph. And then I'm going to look at y equals 0 to y equals, I'm actually going to go up to 68 so that the vertex isn't sitting directly on the top of our screen. And we're going to make our tick marks 4. Okay, so if we look at a graph, there it is. And there's a couple of things you can do at this point. You can use trace. So you can hit the trace button right below the screen, and then you can just type in, say for example, 0.4, and if you hit enter, it will calculate a y value for you. So we got a 58.24. I'm going to jot some of these down. Oh, that was for 0.4 though. And we also want to know what's happening when x is 0.8, so that's 62.36. And we're going to divide all that by 0.4, 0.8 minus 0.4, so that's going to be divided by 0.4. And we can continue. I do want to show you another tool that's really handy. The table is another good way to do this. So I would go into table set. So I'm going to hit second and window, and that gives me the table setup. And I really like to just set mine to ask and then auto. The rest of it doesn't even matter when you set it this way. This means you'll tell it your x value, and then it will tell you your y value. So it's kind of like what we were doing with trace. And then if you hit second graph, it'll take you into your table. I'm just going to go ahead and delete these. Okay, so I was interested definitely in what was happening when x was 0.4 and x was 0.8. We've already got those. I'm also interested in what's happening when x is 0.7 and 0.79. Okay, let me put some of those down and then I'll move on. Okay, so this one is going to be the 62.36 minus 0.7, 62.56, and that's divided by 0.8 minus 0.7. And then here we're going to have 62.36 minus 63.294, and that's divided by 0.01. And then we'll need to know what we get when we plug in 1.2 and 0.9 and 0.81. Okay, so let me put those down. So we're getting, let's see right here, 60. Where did we go? Oh, they're going to switch up on me. Okay, so 1.2 That gave me 63.36. So that's plugging in 1.2. Plugging in 0.8 gives us our 62.36. And then 1.2 minus 0.8, that's 0.4. And 0.8 to 0.9, 0.9, when we plug that in, gave us 63.84 minus 62.36 over 0.1. 0.9 minus 0.8 is 0.1. And then this last one, when we plug in 0.81, we get 63.42 approximately minus 62.36, and that one we're dividing by 0.01. So this is slightly tedious, and you will have some on your homework where you have to do a few of these calculations, but the idea is if we can kind of check out a pattern here, we might be able to make some good conclusions. So now I'm just going to crunch through some of these. So we had 62.36 minus 58.24 divided by 0.4, which gives me about 10.3. Ooh, and I crunched these before, so I could check myself too. Let me make sure that looks like a good one. I totally did not get that before. Okay, let me just double check. 62.36. Let me go back in my table. Oh, these are all 63.36. 63.36. Okay, what's that one? Okay, so then